So we've done some limits now using graphs. We've done limits using tables. We've now done some algebraic limits where we do some manipulations to find out limits. We've also used some arguments for endpoint behavior of strong over weak and looking at the relative strength of functions. And we also now have some established limits. And one of the really important established limits that we're going to use is this one here. The limit as x goes to 0 of sine x over x is equal to 1. Now that is going to be an identity, and we're going to use that now as an established limit. So we can use that established limit to evaluate limits like example 7. So we have the limit as 3 sine x over x squared plus 2x as x goes to 0. What we want to do is we can't really cancel things out here. We can plug it in. We're going to end up, if we substitute in, we get 3 times sine 0 is 0. And on the bottom, we get 0 squared plus 2 times 0, and that's 0 over 0. And we know that 0 over 0 can be anything. We need to get rid of that divide by 0. And we're going to do this by teasing out a sine x over x. So I'm going to rewrite this. I'm going to say this is a limit as x approaches 0. And I'm going to take that 3 out to the outside. So I'm going to take that 3 outside, put it out here. And I'm also going to take that sine x, and I'm going to factor out the x out of the denominator. So I'm going to get sine x in the numerator. And I'm going to factor an x out of the denominator. And I'm left with x plus 2. And notice that we end up with sine x over x. And I can evaluate that limit as this established limit. As x goes to 0, it's a two-sided limit, it's equal to 1. So here we then going to split this up. I'm going to end up with my 3 times the limit as x approaches 0 of sine x over x. That's our identity here. And then we also have the limit as x approaches 0 of 1 over x plus 2. And we know that from our limit properties, we can split these up. So we end up with 3. That limit now of sine x over x is equal to 1. And then we can evaluate this limit as x goes to 0. It's going to be 1 over 0 plus 2, or 1/2. And so our limit ends up being equal to 3 over 2. So if we were to graph this, you should check it on your graph. 3 sine x over x squared plus 2 is going to have a hole at y equals 1.5. At x equals 0, y equals 1.5. So this is using an established limit. For example, 2a, we can look at this and we want to get rid of, well, first of all, let's check this. So we plug it in. We're going to end up with h going to 0. We get negative 3 squared times 2 minus 18 is going to be 0 in the numerator, and replace the h with a 0 in the denominator. We can't evaluate that. We need to get rid of that divide by 0. So what we want to do is algebraically rearrange this. So what I'm going to do is I'm going to expand that out. So I end up with the limit as h approaches 0. We end up with 2 times, I'm going to expand that out to get 9 minus 6h plus h squared minus 18 all over h. We know that if we do the 2 times 9 and the minus 18, they're going to cancel out. So I'm going to end up with limit as h approaches 0. So I'm going to end up with 2 times negative 6 is negative 12h plus 2 times h squared. The minus 18 and the plus 18 cancel out. And so we'll end up with divided by h. We can cancel out a factor of h. So we end up with a limit as h approaches 0. This is going to end up being negative 12 plus 2. One of the h's cancel out, so 2h. Now we don't have a divide by 0, so I'm going to evaluate that limit. And plugging in the h as 0, I end up with a limit equaling negative 12. So we'll do a similar thing here. We're going to expand this all out. So the limit as h approaches 0. Now, these last two, example A and B, these are ones where we're going to see notation that looks similar to this. So we want to get you guys used to using this notation. We're going to expand this out. So we end up with 4 plus 4h plus h squared plus 3 times 2 is 6. 3 times h gives us a 3h, and then minus 10. That's all divided by h. And what we want to do is we want to algebraically rearrange this to try to get rid of that divide by 0. And just grouping a few things here, I've got a 4 plus 6 minus 10. That's going to all cancel out. So we end up with factor of h, which we can see is going to cancel out. So limit as h approaches 0, 4h, now let's combine those like terms. So 4h and 3h is going to give us a 7h. H squared, so plus h squared, all divided by h. That's going to simplify to 7 plus h. We're going to plug in h is 0, so our limit is equal to 7. This next one is very similar. We're gonna plug in our 5 plus h into that expression. So I've got my f of x. There's my f of x. I'm just going to replace my f with the x in my f of x with a 5 plus h, and then I'm going to evaluate that expression. Okay, so this is using that function notation. So rewriting this, I get limit as h approaches 0. I'm going to replace my 2x squared plus 3. I'm going to apply my function notation. So the 5 plus h goes inside, minus 2 times x squared plus 3. I'm going to make sure I put that in brackets so I don't lose that negative. And I'm going to plug in the 5 into that part. So there's my f of 5 plus h minus f of 5, and that's all divided by h. And when we evaluate this, we're going to end up with basically 53 minus 53 over 0. So we have our 0 over 0, so we need to get rid of that divide by h. To do that, we want to expand and hopefully get rid of the constant so that we have a factor of h to cancel out. So this becomes 25 plus 10h plus h squared plus 3 minus, this is going to be 50, and then minus 3. Okay, so we can see that there's some things that are going to cancel out here. And the nice thing is, this usually works out quite nicely because we can see that we have a 50 minus 50, 3 minus 3. Okay, so I'm going to show some steps here. So the limit as h approaches 0, this is 50 plus 20h plus 2h squared plus 3 minus 50 minus 3. Again, we can see that those parts cancel out. These are all going to cancel out. And then we end up with a limit as h approaches 0 of 20h plus 2h squared all over h. We can get rid of our divide by 0. And we end up with 20 plus 2h. Substituting h as 0 now, we get the limit is equal to 20. And so this is the same thing. We're going to use function notation. So we have our f of x function defined as x cubed. So we're going to use our function notation with that. So we end up with a limit as h approaches 0. And now we're going to end up with x cubed minus x cubed as well, where we're going to substitute in 1 plus h and 1 for the second function. So I'm just applying function notation here. And what I want to do is, well, first of all, just check if I substitute in the h is 0, I get 1 minus 1 in the numerator, 0 in the denominator, so I get my 0 over 0. So I need to get rid of that divide by 0 somehow. So limit as h goes to 0, expand this out, 1 plus 2h plus h. Oh, I need to expand that. Okay. So I can use a cubic expansion for this. So it's going to be 1 cubed plus, coefficient is 3, h squared plus 3h plus h. Oh, sorry, I got that backwards, don't I? It's going to be h and then h squared plus h cubed minus 1. Okay, so this represents the cubic expansion using, and what I did is I used a shortcut. I used the binomial theorem to expand this into this. And that's all over h. I've got parts that cancel out. That cancels with that. Okay, and now I have h terms that will cancel. So limit as h approaches 0 is going to be 3h plus 3h squared plus h cubed, all divided by h. I can now get rid of that by dividing by that h. So I get 3 plus 3h plus h squared. Replacing h with 0, I can evaluate that limit. That limit is equal to 3.